Welcome to Lesson 8 of the GAMS training. In this lesson, we will introduce the user to Computable General Equilibrium modeling. This is really just an introduction where we will cover some essential aspects of CGE modeling without going too deeply into economic theory. We leave that task up to the user. Until now, we have presented examples of partial equilibrium models where the objective was to solve optimization problems subject to constraints. But GAMS is also widely used to solve computable general equilibrium, or CGE models. We will illustrate with a very simple CGE model developed by Antoine Bouet. We start with an overview of the mathematical structure of a CGE model. In this simple model, we assume an economy that produces one commodity and uses two factors of production, labor and capital. We assume also only one agent whose income derives from the supply of factors of production and whose total income is spent on the one commodity produced. Finally, we assume that all markets clear commodity and factor markets. In mathematical terms, we represent output y using a Cobb-Douglas production function as a functional form. We express this function in its simplest form. Y is equal to a constant, times kd raised to the power alpha times ld raised to the power 1 minus alpha, where y is total production, a is a scale parameter, and alpha is an elasticity parameter. Kd and Ld are the demand for capital and labor, both expressed in physical terms. We derive factor demands from the first-order conditions of a cost minimization problem subject to output y. Labor demand is expressed as a share of the value of production, or income, divided by the price of labor, W. So labor demand increases with the price of production, P, but is inversely related to the price of labor, W. In the same way, capital demand is expressed as a share of the value of production divided by the price of capital, R. So capital demand increases with the price of production, P, but is inversely related to the price of capital, R. P is the price of the commodity, W is the remuneration of labor, and R is the remuneration of capital. We can now compute national income and total consumption as follows. Income is the sum of the remunerations for labor and capital. Consumption or demand is simply income divided by the price of the commodity produced, where income is a national income and C is national consumption or demand. We assume each market to be in equilibrium, meaning demand must equal supply in the commodity and factor markets. So consumption equals output, capital demand equals capital supply, labor demand equals labor supply. We assume that the supply of capital is 3,000 units and the supply of labor is 7,000 units. So Ks and Ls are set as exogenous variables, meaning they are fixed. In other words, we have now 8 equations and 8 endogenous variables. We do not count the 2 exogenous variables, Ks and Ls. At this time, we want to demonstrate that given a system of equations with 3 equilibrium conditions, If two are satisfied, then the third one is automatically verified. This is what we call Walras' law. We give a proof of Walras' law from equation 5, where consumption C equals income divided by the commodity price. We can bring the price variable to the left-hand side of the equation, and we get that P times C equals income. But since the commodity market is in equilibrium, meaning supply equals demand, or C equal Y, as in equation 6, then we can replace P times C in equation I by P times Y and obtain that PY equal income. We now combine last equation II with equation 4. In equation 4, income equals the sum of labor remuneration and capital remuneration. We replace income by P times Y. We obtain equation III, which says that PY is equal to the sum of remuneration of labor and capital. Now from equations 2 and 3 on factor demand, LD is equal to 1 minus alpha times PY over W, and KD is equal to alpha times PY over R. We can bring factor remuneration rates, W and R, to the left-hand side of the equations. When we add both equations, we obtain equation IV, which says that PY is equal to the total value of factor demand. In other words, using equations III and IV, we can show the following equality of equation V, which says that PY is equal to the total value of factor supply and is equal to the total value of factor demand. If the labor market is in equilibrium, meaning LS equal LD, then we can replace LD by LS in the value of factor demand. And we obtain equation VII, where the value of capital supply equals the value of capital demand. And the third equilibrium condition, capital supply equal capital demand, is verified. So we have shown that given the system of equations specified in our model, if the commodity market is in equilibrium and the labor market is in equilibrium, then the capital market is in equilibrium. We have just shown that in our model of 8 equations, if 7 are verified, then the 8th one is verified, meaning we have 7 independent equations. When solving a system of simultaneously linear equations, equations must be independent in order to give a unique solution. But if we withdraw one equilibrium equation, we will have 7 equations but 8 endogenous variables. We will end up with a model that is not square. We remove one equilibrium equation, for example, the equilibrium equation for the capital market. We now have 7 equations. Note that we could have chosen any of the other 2 equilibrium equations. The model could solve for an infinite set of prices, as long as the price relationship specified by the system of equations in the model is maintained. We can express all prices in terms of any one given price, to which we refer as the numerator. For our purposes, we select P. Next, we write the model in GAMS. We will now go through the programming of our small CGE model. Typically, we can divide the program into 4 main parts: calibration, model, initialization, and resolution. In the calibration process, we define sets, parameters, and introduce the data. We also calibrate or derive the behavioral parameters and other benchmark variables, combining known data and the algebraic relationships defined by the system of equations. In other words, the calibration process implies that the information we have about the economy is consistent with the system of equations defined in the model, and that our benchmark values represent a solution to this system. We start with a definition of parameters, since we do not have any sets in this simple model. Remember, only one commodity and one agent. We define first parameters related to the Cobb-Douglas production function, alpha and A. Next, we also add a set of parameters which will store the initial values of program variables. So to differentiate the benchmark parameters here on the left from model variables of the same name, we add a 0 to each variable name. Remember that parameter values do not change with the resolution of the model, while variable values do. We will define variables later on. In our example, the only known values are the total supply of labor equal to 7,000 units and the total supply of capital equal to 3,000 units. Recall that previously we referred to these variables as exogenous. As discussed previously, the model can solve for an infinite set of prices. Prices are treated as index numbers and can be set initially at any value. Of course, the relationship between these prices must respect the constraints formulated in the model equations. For simplicity, we set commodity and factor prices to 1. In GAMS, we assign 7,000 units to the supply of labor and 3,000 units to the supply of capital. We also set benchmark prices to unity. So we have assigned value to all these variables. We still have to assign values to the other benchmark variables and to parameters alpha and A. To do so, we use the mathematical structure of our model. Equations 7 and 8 state that demand equals supply in factor markets. KD equal KS, LD equal LS. So we can easily calibrate KD 0 and LD 0. Next, equation 4 computes total income as the sum of labor and capital incomes. Income equal remuneration of labor plus remuneration of capital. We can now calibrate income 0. From equation 5, consumption is income divided by the commodity price. So now we can calibrate C0. Finally, equation 6 states that demand equals supply in the commodity market, so C equal output. We can calibrate Y0. Note that the order of calibration is very important. Given that KD0 and LD0 are calibrated from KS0 and LS0 respectively, KS0 and LS0 must be defined first. Similarly, all parameters on the right-hand side of the income equation must be defined before income 0. and so on for C0 and Y0. We finally need to calibrate the Cobb-Douglas parameters. If we solve equation 3 for alpha, we obtain alpha equal remuneration of capital times capital demand over P times output. We can use benchmark values for R, KD, P, and Y to compute alpha. Similarly, isolating the parameter A in equation 1, we obtain the value of A, and we can use benchmark values for Y, KD, LD, and the derived value of alpha to compute A. Note again that the order of calibration is very important. R0, KD0, P0, and Y0 must be defined before alpha. Similarly, for A, all parameters on the right-hand side, including parameter alpha, must be defined before A. After the calibration of parameters and benchmark variables, we define the model. This part of the GAMS code typically includes two main parts: definition of the model variables and definition of the model equations. To be consistent with the model mathematical structure, we must define 10 variables. Recall our earlier discussion on Walras law. We showed that we could drop one equilibrium equation if the other two are satisfied. To do this and still verify that our model is consistent, we add an extra variable which we call Leon in reference to Walras' name, but you could call it anything. We use this variable to verify that the market equilibrium for the redundant or dependent equation is satisfied. More about this later. As we have 7 endogenous variables, we must define 7 equations. Each equation reflects the corresponding mathematical structure of the model. For a review of the syntax, we refer you to earlier lessons. Again, given Walras' law, we define an extra equation, Leon EQ, that sets the added variable Leon to the gap between demand and supply in the capital market, which, as you recall, is our redundant equilibrium equation. If this market is in equilibrium, then the variable Leon should be equal to 0. If we were to solve the model at this point without first initializing the variables, GAMS will try to find a solution with initial values of all the variables set by default to 0. In other words, GAMS will start the process of finding a solution with values of variables very far from their solution values. This would make the solver work harder and much less efficiently. It is a common practice in CGE modeling to initialize each variable to its benchmark value. In this way, assuming the calibration has been done properly, the solution of the model is simply a replication of the benchmark values. The solver does not have to work too hard to solve the model. We initialize the model variables in the following manner. We use the .l suffix for endogenous variables, and we assign to the variables are starting values, the calibrated benchmark values computed previously. We use the .fx suffix for exogenous variables. So labor and capital supply are fixed at their benchmark values. And the price of commodity Y, selected as a numeraire, is also fixed. Finally, the last part of the program is the model resolution. Remember from previous lessons that we first define the model to be solved using the model command. We specify the name of the model, cleverly named CGE, and we want the model to include all the equations. Next, the solve command. We specify the solver CNS, which stands for Constrained Nonlinear System. Note that this solution procedure requires the model to be square. In other words, the number of endogenous variables must equal the number of independent equations. Now, run your program in GAMS IDE, either by pressing the short key F9 or by using the red arrow icon. If your program is error-free, this is what the process window should look like. Note that the invincibility at the input point should be equal to 0. The invincibility value represents the largest gap between the left-hand side and the right-hand side of the equations, given the values assigned to the model variables and parameters. So a value of 0 confirms that the values assigned to parameters and variables are solutions to the system of equations in the model. In other words, it confirms that the calibration was done properly and consistent with the model structure, that the equations were written correctly, and that all variables were initialized correctly. If you look at the solution values in the list file, you will see that they replicate the benchmark values of the variables. These are the values at benchmark for all the variables in the model. Now let's try to run a simulation. For example, assume an increase of 10% in labor supply. To simulate a 10% increase in labor supply, simply multiply the benchmark value LS0 by 1.1 in the assignment statement for the exogenous variable LS. Run the model again, either by pressing the F9 key or by using the red arrow icon. If the model is error-free, the process window should look like this. Note that the infeasibility at the input point is not equal to 0 anymore. This is not surprising, since by introducing a shock, the benchmark values are not solutions to the model anymore. Nevertheless, you can verify that GAMS found a solution. After the shock, the solution values for the model are different from the benchmark values. This is what you will see in the list file. These are the new values for the variables in the model following the simulation. Verify that the variable Lyon is very close to 0 in the case here. If not, you must check for errors in the calibration of parameters or the initialization of variables or in the definition of equations. GAMS is widely used for CGE modeling. In summary, when building your own CGE, you should write the mathematical structure and verify that the number of endogenous variables is equal to the number of independent equations. Keep in mind, walrus law, your model should be square, but should consist of independent equations only. Calibrate every parameter and benchmark variable based on your data sources and according to the system of equations in the model. First, make sure your model replicates your base data. Then, when running simulations, verify that all markets remain in equilibrium by checking that the additional variable Leon remains very close to 0. We conclude Lesson 8 of the GAMS training, and for your assignment, write the GAMS code of the model just presented, run the model and verify that it reproduces the benchmark values, run a few simulations, and verify that Leon remains close to 0 in all cases.